Welcome back, Physical Science 20. So now we'll look at some applications of limiting reagents. So why should we care about limiting reagent? Companies that want to reduce both their cost, so the cost is a factor, and impact on the environment. I didn't mean the cross that, I just meant to underline it. But those are two things that are very important here. So looking at cost, if you own a company, and of course impact on the environment. So chemical cleanup crews consider the proportions of reactants in their work. Also, anyone who burns hydrocarbons as a heat source should pay attention to the fuel-air ratio during combustion. So we'll look at the cost part of it first. So companies often choose the most expensive reactant to be the limiting one. So there's no waste. So there is no wasted leftovers. We want to be able to use it all up, while a large excess of the least expensive is available. So if you want to have leftovers, make sure it's the cheaper one. This strategy helps ensure that none of the more expensive chemicals is left over and wasted. Cisplatin, for example, is an important drug used in chemotherapy treatments for various types of cancers. The process to make it involves 4 chemical reactions. In the first reaction, a compound called potassium tetrachloroplatinate, which is this right here, is added to a solution containing a large amount of potassium iodide. If you own platinum jewelry, you know that platinum metal is expensive. Platinum compounds such as this are very expensive. So as we'll see here, we'd likely want this to be the limiting and this to be excess, because we want to make sure that all of this gets reacted to produce what I want it to produce, and that none of it is wasted. So if you look at the next page, it's cheap. So using a large excess of potassium iodide is okay because it's cheap, to ensure that all of that potassium tetrachloroplatinate is used up and converted into products. A large excess also increases the likelihood that all fluorochlorine atoms in the platinum compound are replaced by iodine. Once the limiting reaction is used up, the reaction stops. In this step of the cisplatin production process, K2PtCl4 is the limiting reagent, as I mentioned, because it's the expensive one. We want to make sure we use it all up and have no leftovers. It's okay to have potassium iodide left over because it's a heck of a lot cheaper than K2P2Cl4. Okay? Looking at reducing environment impacts, controlling the limiting and excess reagents can make manufacturing processes greener. Metal smelting is a major source of sulfur dioxide, a pollutant that reacts in the atmosphere to cause acid rain. Flash smelting involves burning ore concentrate in large excess oxygen. The oxygen reacts with the sulfur, forming sulfur dioxide. Because there is an excess of oxygen, sulfur is limiting, and it's all going to be converted into sulfur dioxide, and of course oxygen is going to be the excess. It is economically feasible to collect the sulfur dioxide gas and convert it into something like a useful product such as sulfuric acid that can be used in the lab. Environmental cleanup is also a reason why we care about limiting reagents. Strategies used to clean up or neutralize pollutants in the environment can involve limiting and excess reagents. So consider, for example, the treatment of water contaminated with toxic metals, like we've talked about before. One way to remove metal ions is to precipitate them as metal hydroxides. So we talked about that back in the single replacement and double replacement area. This can be done by adding excess base, such as sodium hydroxide. In the following example, toxic lead ions that are dissolved in water, so that's why they're showing up as lead 2, will combine with hydroxide to make this. So of course, this would be whatever we have in the water. We want to be able to use it all up. And of course, the material that you want to use up is the limiting reagent. And this we would have in excess, leftovers, to make sure that all of this gets used up. Also in the lab, if we spilled some hydrochloric acid or sulfuric acid, baking soda would help neutralize this. And maybe you saw me do that when neutralizing acids. So spills of concentrated acids or bases can be neutralized by adding a slight excess of sodium hydrogen carbonate, or baking soda is what it's known as. So that's going to be excess because it's cheap. And we want to make sure that we neutralize all of the acid. So the acid would be labeled as the limiting reagent, and this would be the excess. It's okay to have this left over. It's not okay to have this left over, though. A more basic substance such as sodium hydroxide could also be used. However, a stoichiometric base must be used if we're using something more basic, because that could eat through the tabletop, etc. So baking soda, though, we have a lot of it. You can use up as much as you want of that. And also, if we used up too much of a more basic solution, it would become basic, and that could affect things too. Improving fuel efficiency is another reason why we care about limiting reagents. We usually want to the most possible energy from our furnaces, our car engines, and our burners. Complete combustion, as we talked about, releases the most energy. And we did that demo in which we lit hydrogen and oxygen in an incomplete reaction and a complete reaction. We saw we got the bigger bang with the complete combustion reaction. We therefore want our fuels to undergo complete combustion rather than the less efficient incomplete. And of course, to ensure complete combustion, we have to ensure that we have enough oxygen, and usually we're getting that from the air. So oxygen is the excess reagent with burning something or combusting something. Complete combustion of different fuels react in different stoichiometric ratios. For example, some barbecues burn methane while others burn propane, which requires more oxygen. So if we look at it here, the more complicated, so methane is CH4, propane is CH3H8, heptane is C7H16, and you can see here oxygen amounts. The bigger the molecule is, the more oxygen you require to have complete combustion. So that table kind of summarizes all of that. And of course, devices used for methane, such as a burner. Devices used for propane, such as a barbecue. Devices used for heptane. Your car are built specifically to allow for enough oxygen to have a complete reaction there. And of course, we try as best as we can to make the fuel the limiting reagent, and we try to get oxygen as the excess. Okay? So of course we can't use propane in a car, and we can't use gasoline in a propane tank because those devices are not built for that. So that's kind of what I talk about in this last paragraph here. Just the devices used to ignite each one of these are different because they try to ensure that we have as much oxygen as we possibly can in order to ignite it. Okay, I'd like to take a look at the assignment, and in particular number 3. I want to discuss this one. So the figure below, or actually it's over to the right, shows the result of an experiment in which different masses of magnesium are combined with identical volumes of hydrochloric acid. We get hydrogen gas being produced, and it inflates the balloon. The gas goes into the balloon and makes it bigger. Okay? So we have HCl and magnesium, and of course you can tell, oh, that's a single replacement reaction. So we have the magnesium, it's more active than hydrogen, so it replaces it, giving us hydrogen gas and magnesium chloride. So of course that's a single replacement. And in this chart here, identifying the limiting and excess reagents for each trial. So if we take a look here, to kind of figure this out, compare trial 1 to trial 2. So here we have 50, 50, 50, 50. So we have 50 mils of hydrochloric acid throughout. In this first one we have 0.2 grams of magnesium, then 0.4 grams of magnesium, then 0.6 grams of magnesium. So you can tell here that I'm adding more magnesium and I get more gas being produced. So remember, it's always the limiting reagent that determines the reaction. So magnesium must be the limiting reactant in all of these, because the more I add, the bigger, or the more gas that is produced. So in trials 1, 2, and 3, magnesium must be limiting, and hydrochloric acid, I must have more than I actually need, because the magnesium seems to be the thing that's affecting it. And we can say magnesium is used up for all of those. And we could also say here in this column that magnesium seems to be the reactant that's determining how much gas is produced. Okay? And then when we go here, we go from 0.6 magnesium to 0.8 grams of magnesium, there's no change. So the magnesium doesn't seem to be affecting it anymore, which means that we likely ran out of HCl. So and I could add 0.1 gram of magnesium, we would get the same thing. So it looks like things have switched. Now the HCl is the limiting reagent, and the magnesium is excess. And we could simply write here, HCl seems to be used up since the balloon doesn't change anymore. Okay? So that's kind of that's one of many examples we could talk about there, in which if we add more of one substance, then it flips from what was the limiting reagent, now becomes the excess reagent. All right? So you should be able to do the rest of that assignment. It's very similar to what we talked about on the notes, and we'll see you again.